Okay. Okay. Let's see. This was what I was trying to pull up. Okay. And it's just talking about our solar system, and it's kind of fun. You can pick which planet you're interested in, and okay. But it's got the most annoying music. Indeed. The other one is actually the Cosmos series. Has a look at kind of what they call a cosmic calendar. So maybe we'll look at that here in a little bit. Okay, our solar system at a glance. Okay, and we're going to kind of walk through it. This chapter, actually, we're going to talk about the planets. So if you're this chapter, I'm at this unit. We'll talk a little bit about planets in this chapter, but actually we're going to hit the planets hard next week. Talk about the terrestrials and then the gaseous planets a little bit. And the sun is going to be the next unit of material. But the sun is converting, takes a little bit of matter to make a lot of energy. I think E is equal to mc squared. I kind of looked at that before. Kind of mentioned that before. So the first planet from the sun is Mercury. And Mercury looks a lot like the moon. And on these slides, actually, next week when we talk about Mercury and when we talk about these planets, already on these slides you kind of see some of the highlights about these planets. Okay. So one thing, I don't know if it strikes you too, but do you see where it's like so, it goes, you think it would be pretty hot, right? You think that that planet would be pretty hot. But the thing is that it rotates so darn slow that the side of the planet that is away from the sun is very cold. So that's what Mercury's got going for it. And then Venus is just hot all the way around. Okay. And then, of course, Venus's big thing is, and we'll hit it again next week, but hopefully we're going to, I don't know if you can kind of see these clouds here. Okay, you can't really see the surface of Venus like you can see the surface of Mercury. And those clouds create an intense greenhouse effect. So it's just hot, hot, hot. Sometimes Venus has been called Earth's sister. I know we think of Mars as Earth's sister, but Venus is kind of closer to Earth than Mars. Then we have the Earth. And one of the things we're going to talk about in this chapter is that the Earth's moon, I'll put a question mark there. Okay, we should not have such a lovely moon. Okay, it's big and beautiful. Well, actually, just because it's big, kind of things that are big in given time, they kind of round out. So it's big and spherical. And you're like, dude. So that's the Earth. And then, of course, we have Mars.
You go back.
Oh, I sure can. You're fine. So as far as we know, this is the only place with big life or little life. But we keep looking on Mars for life. And did you guys see that? And my husband was pointing it out to India. The first time Bada Boom actually had a successful cheap mission to Mars. So, hooray for India.
And weren't we sending another something out here just recently?
Yeah, I think, is it Maven? Is ours Maven? I think it's where we're going to look at the atmosphere of Mars to understand but yeah, amazing. And then, of course, we begin our big planets. So Mars is the last terrestrial planet, rocky planet, and then our giants, our gas giants. Jupiter is the first one. And actually, it's the biggest of the 4 gaseous planets. Okay, and there, I don't know if you see, and we'll talk more about this, but this is the red spot, great red spot. Should put the word great in front of there. And that is a storm that's been going on. So we're not looking at anything rocky. We're just looking at clouds. And that storm's been going on for over 300 years. So when we start with Jupiter, then all of those giant gaseous planets have moons. And so remember that image we saw kind of with and without adaptive optics, Io? This would be kind of like you're on Io looking back at Jupiter. So this is one of Jupiter's moons. Okay, so the 4 moons that Galileo saw are right here. So these are the Galilean moons. Actually, it's right there. These are the Galilean moons. Io, Europa, Ganymede, and Callisto. Do you remember in that chapter where Galileo made Jupiter like the symbol of a star? And then he showed kind of the moons orbiting Jupiter. And actually, if we're going to find life, I bet it's quite possible it's going to be on one of these gaseous planets' moons. So Saturn, beautiful Saturn. And this is kind of pretty. This is actually Saturn's shadow. If you see a picture like this, kind of picture the sun must be over here. Okay, and basically this part is casting a shadow on its rings. Isn't that cool? Actually, I guess the sun should be down here. Final answer, because this is illuminated. And this over here is another very important moon of interest called Titan. We've landed on Titan. Does it look kind of fuzzy? Titan has an atmosphere, okay, and they're thinking, actually they think it has a cycle of clouds. It's not H2O, but it's methane. It's kind of interesting. And then Saturn actually, that makes the pretty disk of material, kind of looks like almost like a skirt around Saturn, and it is around its equator. Saturn's rings aren't solid, as you might imagine. They're kind of like little rocks, chunky rocks. Did you guys get that? Okay. See? Uranus. And one of the things, if somebody has drawn Uranus correctly, and I think I mentioned this before, this is its axis of rotation. Okay? So its axis of rotation is almost lying in the plane of the ecliptic. You know, our axis of rotation is tilted 23.5 degrees from being perpendicular. Okay, and it's like, okay, so we think it just got knocked. So Jupiter and Saturn are kind of like twins, and Uranus and Neptune are kind of like twins. Uranus and Neptune are blue for the same reason, and the reason is, I think it's methane, CH4. You see the rings, though? And it also has moons. Oop, I didn't do that. And so Uranus and Neptune, they both have that same blue color. And a cool moon around Neptune is Triton. One of my things, I don't like it when words sound alike. So Triton is around Neptune, but Titan was that cool moon around Saturn. So I will just go ahead and point that out. Triton and Titan. All right. And New Horizon is on its way here. And I think it's going to be next summer, like July-ish. So I think it's 7/2015.
How long does it take to get there?
I'm wanting to say 7 years.
Oh,
I know. Yep. So it's a while. It has all sorts of, I was listening to a podcast the other day that talked about sending things into outer space. And they have to do all sorts of kind of gyrations to basically get momentum. They kind of steal a little bit of our orbital, or I don't know, throw them out. So it's a trajectory thing. All right, so that's just kind of the quick and dirty of what's in our solar system. Okay, so it's a dance. It's like a planetary dance, and at the center is the sun. So now we're going to talk about kind of how our solar system came to be. And just like the scientific method of reasoning, just like the common day method of reasoning, you make observations like this, and you have to keep that in mind when you go about explaining stuff. So for instance, however we talk about our solar system was formed, we need to recognize that, I usually say counterclockwise, don't I? Counterclockwise, yeah. So it's all about the planets orbiting the sun counterclockwise, and for the most part, it's all about planets rotating on their axis counterclockwise. Okay, so that's one clue. And then another thing is that we talked about kind of the 4 rocky ones, and then we begin the gas giants. The gas giants are called Jovians. So if you hear somebody talk about a Jovian planet, they're talking about a gas giant. Okay. So whatever explanation about the formation of our system of planets, about the sun, we need to explain that there's 2 types. So you can't stand on the surface of Jovian planet. When we talk about them later, we're going to see that we really think that at the heart of Jovian planets, it's almost like they swallowed a terrestrial planet. It's like kind of creepy. Another thing, let's not forget the miscellaneous stuff. So I think we talked about this before briefly when I said that Pluto got demoted. This has to do with Pluto's demotion. Basically, Pluto begins a region we call the Kuiper Belt. Can you see the typical Kuiper Belt comet orbit? Okay. Pluto, honestly, we think is an icy body, kind of like a comet. Okay, it just happens to be in a it's spherical because it's hefty enough, and it just happens to be in kind of a nice little pattern orbiting the sun. So we need to explain those miscellaneous things. Okay, and the Kuiper Belt I mentioned, this is where actually Pluto is one of these. Pluto's a member of those. And then we have something even farther away called the Oort cloud. And the contents of the Kuiper Belt and the Oort cloud are very similar, kind of rocky, icy stuff. But the Oort cloud is just crazy with the sun at the center, just way out there. Okay. So I said, this says we need to account for exceptions. I already told you, remember I put like a question mark over our moon? How lovely it is. Okay, but how did we get such an awesome moon? You might be thinking, and I'll try to kind of remind you as we talk about the rocky planets, the terrestrial planets. But you might be thinking, who else has got moons, right? Mercury, no moon. Venus, no moon. Earth, one beautiful moon. Mars, 2 ugly potato-looking moons. We think they were just kind of accidentally, like little chunks, kind of got too close to Mars and other episodes. Okay, so why do we have a beautiful moon? And then another exception is if this is Uranus, okay, Uranus's axis of rotation kind of lies in the ecliptic. What the heck is up with that? Okay, and then we can kind of, we'll account for that. So, do you remember when I talked about different types of objects up there? And I said one object was what we call a nebula. Okay, there are planetary nebula. There, like tonight, if the skies cooperate, we're going to see a ring nebula. It's a type of planetary nebula in the constellation Lyra, where hopefully we're going to see that quartet. But a nebula basically is in outer space, and you run into a pocket of gas and dust. Most of outer space is nothing. So a nebula is like, oh yeah, I like this. So the thing about nebula is they're great, and we're going to talk about how a nebula can foster the formation of a star and a system of planets around that star. So basically, as we talk about our solar system being born, we talk about it being born in a nebula. Okay? So the nebular theory, we're breaking into the formation of our solar system. Okay. Oh, sorry. Nebula. So there are big nebula and those are small nebula. We're talking about big nebula if it's going to form a star and a system of planets. So this says galactic recycling, which is okay, but I would even kind of think of galactic recycling, I would even think of stellar or star recycling. Okay, and they're similar. To me, galactic recycling almost says that, well, recycling means you use it again, right? Okay, and galactic means galaxy. So galactic recycling almost says you get a whole new galaxy out of an old galaxy. But what you're seeing there is you get a whole new star out of an old star, basically. You get a whole new star out of an old star. See the circle of life, just like in, what was that word he holds up, the lion?
Lion King.
Thank you, Lion King, yep. Okay. So we're going to talk about the life cycle of stars, but this is basically showing you stars start out, okay? This actually kind of looks like kind of an early on, not quite star. It kind of has jets of matter, okay? It's like, it's a baby star just kind of getting ready to turn on. That's the way I would think of it, okay? Those jets of matter actually are kind of associated with kind of the spinning motion, this, what we call the accretion phase. So here, right here, this is stable. Okay, stable, that's what I'm trying to write there. So a few slides ago, we talked about our sun being like a stable sort of deal, and it is, on that slide it said it's fusing hydrogen into helium, it's stable. But our star, actually, the sun, is going to die. I'll put that in parentheses. So stars don't last forever. Ours has been stable for about half of how long it can be stable. So it's been stable for about 5 billion years, and it has another 5 billion years, BY, before it's going to do something else. And it's not really going to die, but it's going to turn into a white dwarf. Our sun is. So sometimes we look at stars that blow up, and that's not the path that our star is going to take. It's not going to blow up. It's just going to kind of retire. But even stars that retire kind of slough off. Can you see this stuff over here? Okay. Even stars that retire slough off some material. To me, though, a star that retires slowly, like that, kind of sloughing off its stuff, there's not enough material here to make a new star. Does that make sense? It's like a doomsday story?
Our sun starts dying.
Yeah, it is. It's running out of hydrogen. But 5 billion years, I can't imagine what our race is going to be like. It'll still be here. But it's going to transition, and the whole white dwarf thing, on its way out, it's going to swell. And I think it's like it will overtake this Mars, I think, the orbit of Mars. So, what are you going to do? You know?
Something that said that life on the planet would start to die out in 500 million years because of it getting so hot.
Global warming sort of thing, or?
I don't know, I didn't read the whole thing. But it said that it would start dying out way before the 5 billion years.
Well, there you go.
Our winter's so cold, so we got waste of it.
Yeah. Yeah.
But let's switch to something, things that are bigger than us, okay, bigger than our star, they do blow up, okay, it's called a supernova, okay? And to me, those things, basically, when they take all of their material and scatter them in their explosion, we're going to see they leave a little remnant behind. But those are the things that can basically give their matter back to new stars moving forward. And that would be kind of the recycling part. So, honestly, we know that our sun was made from another star because it has heavy elements. Okay, so I'll,
Heavy what? Sorry.
it has heavy elements. You know, we talked about the different atoms of different elements. So the nebular theory goes like this, and remember, theory means that people in this line of science are cool with it, you know, and things really suggest that this is the real deal. So we have a solar nebula, right? So you can kind of see the contraction with the red arrows and kind of the spinning with the blue arrows. So we have two things kind of going on over time. So this is before our sun was a star. Okay, this is like the fodder that became us. Now keep in mind that solar nebula needs to form the star and the planets. Okay, so we have spinning. And one of the things that we needed to touch on in chapter 4 was this conservation of momentum. Okay, so we had spinning, and as it, we talked about, well, a few things, we talked about a lot of different things, but we said that if you take gravitational potential becomes less and less as an object brings its material in, like we see here, this heats up, which it does. The other thing, the conservation of spinning, the skater, remember the skater, when she has her arms out, she has a certain velocity. When she brings her arms in, she goes faster and faster and faster. So those two things are what we're seeing as the thing is contracting and spinning. So, there we go. Now this is kind of fun. See the term protoplanetary disk? I think it's fun because like we can see stars that are in this stage in the Milky Way galaxy, okay? We can see fellow stars that are, they're not stars, I guess I should say, they're still blobs. They're in the process of becoming a star. And the word planetary disk means that they are going to form little planets. So let me see. I've got several of these. I think they're pretty good. So, see the solar nebula? And similar to this person. So it increases the rotational speed, okay, and actually that kind of, the way the disk was going, our protoplanetary disk or our nebula was going, that actually kind of, that gave us a spin of our planets in that same direction too.
What do you think's going to happen when the sun goes out?
What's going to happen when the sun goes out? Like if we could survive the whole swelling part, or I mean, like on the way out, it's gonna enlarge. It's gonna take. The Earth is gonna fall into the sun. The sun's gonna expand to overtake the Earth's orbit.
So in 5 billion years, our 23 grandchildren are going to fall into the sun and burn up. Yes.
I think that it's possible that we could by then have communicated with aliens. No, we could by then have some way to, to save ourselves. I don't know. But it is kind of doomsday-ish. But according to, you were saying that way before that we're going to be dead.
They've said that how many times already that
Yeah.
Let's hope that this time it's
in
for
year
real.
2000,
So it's for
last
real.
year, December 21st, the whole, everybody was gonna fall off the face of the earth.
You get by an asteroid.
Yeah, different ways to die.
I hated that theory.
This one, it just simply says that kind of random particles are kind of brought in line by the other particles that are in line. I know. So if you look at, it reminds me of like bumper cars. So if you're random bumper car number 14, notice that eventually you're going to fall in line just because of the collisions and the other cars going in that direction. Just kind of makes sense, the way things kind of go down. Now let's look at this one. So this is looking at on the face, and this is looking at on the edge. Again, this would be our solar nebula. Oh gosh, you can't see that one, can you? Okay, the other one. So we see stars doing that. Oh, let's see what next says. Okay. I think you get the idea. Again, just kind of making everything kind of go the same direction. Okay. So now this is a different app. I'll pull this one up too. And let me see. There is a very cool program that you should be able to download called NASA's Eyes. I showed you guys that. But the way this works is you can click any object. That's the sun. Of course, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. And could you kind of see how the information changed as I went across? I mean, they say, okay, start here. First off, you see Mercury's the red line over there? Okay, that's axis of rotation. Mercury's pretty much straight up and down. Okay, now it's kind of cool because next week we are going to talk about why in the heck Venus's arrow is totally upside down. Venus actually spins on its axis. It's a renegade. Venus goes backwards. So if you were going to look at it, it would be going actually clockwise down the North Pole. Okay, I know. And actually, I'm going to kind of walk you through it, but we think that Venus just basically got totally whacked. So it used to do this, and at the time we had as heavy a bombardment in our solar system, totally whacked. It didn't stop like Uranus did. It went all the way down like that. Like, dude, okay? So there's a table in your textbook that has all of this information, but this is just kind of I'll see if at break I can pull up NASA's Eyes. It's really cool. Speaking of, I'm thinking this is get you thinking. Okay. All right. So I already kind of told you the caption for this slide. It says that, hey, you know, how would we even think this nebular theory is correct? Well, we see what we're going to describe happening in other places. So if I were to ask folks one of their favorite constellations, oftentimes it comes down to Orion. And that actually, you're looking at that nebula, is in Orion. It's in Orion's sword. Okay, the belt, the 3 stars that we love, hanging down from that is his sword. So I'm going to kind of zoom in to see baby stars. Oh, I'm going to zoom in. Look for the babies. There's the babies. Okay, the prototype. Okay, those are like not quite stars. Okay, being born in a big old, what we call stellar nursery. Why? Because there's all sorts of gas and dust to be in there to be had to make stars. So a lot of times stars are born in similar locations. It's adorable. Okay, so just again, this slide is kind of emphasizing what we're seeing outside of our solar system going on. You kind of see the disk of material, like we looked at those videos, you know, kind of flattening out, forming our disk that ultimately became planets within the disk and the sun in the center. So here is a stab. It's not a stab necessarily, but we do need to explain why in the heck is Jupiter so crazy different than Mars. Okay, Jupiter's a gas giant. Mars is kind of like Earth. You go stand on it. Jupiter, humongous. You're not standing on Jupiter. Okay. Well, the solar nebula. Now I hope we're all kind of okay with the solar nebula became our solar system. Actually, there was 4 main types of material in our solar nebula, and they're still here today. Okay, so when I talk solar nebula, I think sun, the 4 rocky planets, and the 4 gaseous planets. Notice that, and I like what that last column is because it kind of shows you spatially. 98% of the material in our solar system is hydrogen and helium. And I kind of giggle because honestly, I don't know about you, but helium's not something that I really worry too much about. I don't think of it as part of my, you know, the atoms in my body, the atoms I interact with. Okay, hydrogen, yeah. Hydrogen's in water, right? Hydrogen's a lot in living material. Okay. But that 3rd column there that talks about condense, here's the deal. Hydrogen, it's hard to cool it down to get it to go ahead and go from a gas to a liquid. Have you ever bought liquid nitrogen, or let's see, what's another example? Have you ever bought dry ice? No. Okay, dry ice. Okay, just use your imagination. Dry ice, you used to be able to buy it at Hy-Vee, but basically what's that? You still can? Good. But basically what dry ice is taking carbon dioxide gas and cooling it down and pressurizing it to make it solid. So basically you're taking something we know as a gas and doing extreme cold and pressure and making it into a solid. Okay, that's a type of what we call condensing. Okay, but so carbon dioxide, you can go ahead and get it to solidify. You could get it to liquefy too if you kind of massage the carbon dioxide how you did it. But my point here is there are some things, some simple atoms like hydrogen and helium. You try to cool them down and pressurize them, and it's just not in the conditions that were early. It didn't what we say condense. It stayed a gas. Now if we compare that with this. Okay, so hydrogen, helium, 98%. The next abundance of stuff is exciting. It's compounds. And you know, what compounds is basically a couple of atoms joined together. Let no man put us under. Okay, so 1.4% of the stuff in the solar nebula were these compounds that contain hydrogen. So when we say compounds that contain hydrogen, and sometimes this makes it, when I'm looking for stuff to throw on my test, in the past anyway, hydrogen-containing compounds, water, methane, and ammonia. Okay, 1.4. Now notice that it does condense. Okay, in other words, what that column says is if you get it cooler than 150 Kelvin, 0 Kelvin, I know, it's still cold. Yeah, because we're about 298 Kelvin right now. Room temperature. Okay, so 150 Kelvin's cold. So cooler than 150 Kelvin, that stuff starts taking from a gas and it starts doing something, either liquid or a solid. So that's a lot that's the lion's share of our solar nebula that ultimately became our solar system. So I'll put the other two things up. What's that? The other two things are rocks and metals. Now, honestly, when you get down to rocks and metals, I can almost say, okay, I'm good with that. Metals we have floating around in our body. Assortment of these. I guess they're kind of not a whole lot of them, but our body is made up of, we need water, okay, but that's not very much of the stuff that made our solar system. So now if we focus on this last column, okay, notice that it can stay a little bit toasty and you can go ahead and get condensation or from a gas to a liquid or a solid, okay, at a higher temperature. And that's the significant part, okay? So these solidify at a higher temperature. These don't solidify. This doesn't solidify at all, okay? And this solidifies when it gets cold enough. Do you kind of see all that? Okay. So in a nutshell then, that is how we ended up with rocky planets on the inside, okay? Let's see. So the way this works is, it's kind of strange. Over here is, you are close to the sun, and as I go out here, you're getting out towards where Uranus and Neptune are, okay? So for instance, if I click here, a line shows up how hot it is. If I click here, that's how hot it is. Here, okay? I'm getting farther and farther from the sun. Okay, it's getting cooler and cooler out there. Makes sense? Okay. So very hot near the sun, gets cooler the farther away you are. Now, there are some important lines here. That green line, okay, shows you where, at what point finally it's cool enough outside that green line for rocks and metals to go ahead and start to solidify. That blue line shows you beyond there it's finally cool enough for your water and your methane to go ahead and solidify. Okay? So that blue line is what we call the frost line. And I think this is a good time for a break. If it's dark, there was an iridium flare at 7:35, but I don't think it's going to be dark enough. So let's take a 10-minute break. And we'll try not to get locked out, but I'll show you that iridium flare. Let's see, heavens above, -com. Sperry, that's not where we are. Well, now let's see how bright it is. Ah, it's not as bright. Yeah, at Sperry, it was like a negative something. Here it's a 0.7. So probably not. So 10-minute break or so, guys. Probably not much to see out there.